Hi everybody, this is a video about flat versus globe Earth. I believe in globe Earth, but some flat earthers may say faked space missions and photos. I say maybe, so what? They may say government intrigue, mysterious missile launches, Antarctica off limits. Maybe, but if so, whatever they're hiding, I'm pretty sure it's not a flat Earth. Why do I have a high confidence in that statement? It's primarily about the path of the sun, moon, and stars. These are things you and I can observe and think about ourselves without worshiping science. You may even say better things, more like apparently flat horizons, lasers, and optical experiments. But again, I say interesting. But sorry, they just can't hold a candle to the sun or the moon, but the pun works better with the sun. So let me share my thoughts about it, and do you take them or leave them? This is what the path of the sun looks like in reality. This video is very interesting because the camera was mounted on top of a 24-hour clock to help track the sun better. The basic features are that the sun rises, it sets, it has a constant angular velocity through the sky, and the sun doesn't change sizes. I made this simulation to help demonstrate constant angular velocity. At equinox, the sun rises in the east, it tilts slightly to the south, at least where I live, and sets due west. That's really interesting. At equinox, everybody gets a sunrise in the east and a set in the west, not just approximately, but exactly. Now, the tilt that they see would be different depending on their latitude, but everybody gets these. Each step of this animation corresponds to 15 minutes in the real world. In this observer in the middle, we're going to watch the sun go between the 6 a.m. and 7 a.m. hour. What I'd like you to do, if you like, is to get a ruler and measure the distance on your screen between 6 and 7. And let's go up to noon. And measure the distance between 12 and 1. You'll see that it's the same distance as we had between 6 and 7. Similarly, if we go down to 5 p.m. and 6 p.m., measure the distance between those. It's the same as between 6 a.m. and 7 a.m., or 12 noon and 1 p.m. And that's what constant angular velocity means. It means that every hour it covers the same distance to your eye. In real life, the sun covers 15 degrees every hour of your sight. And the sun travels that same distance relentlessly throughout the day. It doesn't vary. Constant angular velocity is important to think about because you don't normally expect to see constant angular velocity except in certain situations. Either you're observing an object which is moving steadily in a circle, and you need a second ingredient, you are at the dead center of that circle. Or the other possibility is that this could be standing still and the observer could be rotating. This doesn't work if we take the observer out of the center. Let's move him up. Let's re-enter the observer there. Measure the distance between, let's get back up there. Measure the distance between 6 o'clock and 7 o'clock. Now let's go up to 12 noon and 1. Now measure the distance. It's not remotely the same. If we are not at the center, this sun is not traveling the same distance in that hour to our eye as it did between 6 a.m. and 7 a.m. And it's also different between 5 and 6 p.m. So once again, in order to see constant angular velocity, this has to be moving in a steady circle, and also this observer has to be at the dead center. Strictly speaking, mathematical perfection is required. You have to be at the dead center. But in the real world, there's close enough. An area in which you can move around and still view constant angular velocity. Now, we would say that that consists of the whole Earth. We can be in North America and view constant angular velocity, and thousands of miles south in South America, we could view constant angular velocity. And logically speaking, they're not both perfectly at the center of this perceived arc. However, given the scales proposed, with the sun millions of miles away, the zone of good enough covers the whole Earth. The fact that we can see constant angular velocity at two places which are so far apart is proof of the scale of this model that we're dealing with. This sun is far away. So to recap, constant angular velocity typically happens if something is moving in a steady circle and you are at the center of the circle, or you can be the one that's rotating steadily. Constant angular velocity is very hard to fake outside of those two cases. And so when you see constant angular velocity, it's a very strong clue that the motion is angular. On the flat Earth model, we would not expect to see constant angular velocity. Only those in the North Pole area are even remotely near the center of the proposed circular path of the sun. Other places are very close to the edge, or even on the other side of the path of the sun. And constant angular velocity would be impossible to observe. Or that's the way it seems to me. Now, maybe you want to know, is constant angular velocity something that I can verify? The answer is yes. There's a couple of devices called equatorial sundials that you can construct. This is an easy to make equatorial sundial. You just print out this template here, which has the hours spaced at even angles. And then you place a shadow stick through the center. And then place it at a specific angle for your latitude. And that angle is to help align it with the sun. Anyway, you can see the shadow off to the right now. It says it's 6 a.m. And you should be able to see the sun go this same angle every hour. Here's another kind of equatorial sundial you could make. You place the shadow stick at the center of a circle where you've printed the hours, again at even angles apart. And then you watch the shadow of the stick. Let's go back. It's at 6 a.m. 7's hidden, sorry. There's 8, 9, 10 o'clock, 11 o'clock, 12 o'clock, 1 o'clock. Equatorial sundials are devices that you can place in the real world and help convince yourself of constant angular velocity. Besides equatorial sundials, there are other things you can do to help prove constant angular velocity to yourself. You can use time-lapse photos, or maybe there are other things you can do. But once you are convinced of constant angular velocity, which exists in the real world, then you'll have to take my point seriously. You can observe the moon instead of the sun. The moon has some advantages. It's safe to look at, won't damage anything. It doesn't have the same tendency to overexpose your lens and flare wildly like the sun does. One thing that this video is good at showing is the constant size of the moon as it's rising. I calculated that the moon should have changed a noticeable 5 to 10% as it went through this arc based on its size. But instead, the size stays constant, as it will throughout the whole night. And as you go outside and observe the moon yourself, your mind will tell you that the moon is bigger at the horizon, not smaller. That's actually a trick, but it's something that you should think about when deciding whether the moon is so much farther away here that perspective has placed it at the horizon. Instead, I hope you'll come to the reasonable conclusion that the distance between you and the moon does not change dramatically throughout the night, and instead its path is angular. If the distance between you and the moon does change, its size will change. And if it does not, then the only motion possible is angular motion. The fact that the moon's size does not change is extremely powerful proof that the path is angular with respect to you. So we have two witnesses that the paths of the sun and moon are angular. Those things again are constant angular velocity and constant size. Together, those two things amount to big problems for the flat Earth model. What makes it worse is that as the sun and moon set, their angular velocity, which stays constant, is downward. If that does not change very abruptly, then the sun and moon will be under my feet. On the globe Earth, that's no problem. On the flat Earth, it's a big problem because there's ground in the way. So yeah, constant angular velocity says the sun goes under my feet unless it stops very abruptly. And it is my perception that it does go under my feet. That's at least as scientific as saying that to me the Earth looks flat, which is what I hear flat earthers say. And yet I know that when the sun goes under my feet, it goes over someone else's head. And that either means that they are way the heck down here and maybe standing at the same angle as me, but nobody believes that. Or else they're standing at a different angle than I am. See, the sun's over their head. And the cycle continues until somebody standing in Ukraine sees the sun go under their feet, and it's my turn again to have the sun over my head. This is not just pure speculation on my part. I'm a programmer and I work with people in Ukraine. Some of our work is outsourced there. And we have video calls at the end of their day. And we can see the sun setting for them. And meanwhile, it's up for us. Also, I've had coworkers go visit Ukraine personally. By my own experience, I have high confidence that the Earth is globe-shaped, and that either the sun goes around it in a steady circle at a great distance, or else we are the ones rotating. Now, objections about why don't we feel that motion are wrong, but I'm not covering that in this video, and maybe I will in another. Now, to me, it's strongly intuitive that the paths of the sun, moon, and stars don't work on the flat Earth model. Still, I created this animation to really demonstrate it. Here's what the sun or moon path looks like on the flat Earth model. Here's a video of an equatorial sundial placed on a flat Earth model to help demonstrate that constant angular velocity does not work. This is the simulation which produced the render. It's done in a free program called Blender, which you can download and learn. There are a lot of people on YouTube who are willing to teach it, but there's also a lot to learn. I've also made the simulation available for download, so I hope you'll take the opportunity to download it, criticize it in detail, and tell me what's wrong with it so I can improve it. Or better yet, you can fix it yourself and reshare it with us so that we can find out if and where I went wrong. The simulation has about 13 miles per Blender unit, and according to that, I've placed this sun that's rotating 3,000 miles up, and it's at equinox. I placed an observer down in the Salt Lake area. Oops. There he is. Let's enter him. And let's give a few explanations here. This is the sun. This here is a compass that tells you which direction the observer is looking. And there's this little strip here that helps tell what times the sun should rise and set. Right now, we are at noon and we're looking pretty much south, which is as it should be. Let's come over here. That little gauge or strip is turning red, meaning that we should be approaching sunset. And here we are at set, or this is where it should set. But it's still several degrees above the horizon. Also, we're looking more to the north than we should. We should be looking due west at this time. Okay, let's continue on. The sun should be under the horizon this whole time until rise, which is right here. And once again, we were not below the horizon, which is a problem for sunrise. We're also looking considerably north of where we should. We should be looking due east. Also, let's just let it run for a while, and we see that the size of the sun changes on its near and far approach. So let's recap the problems on the flat Earth model. Most glaringly, the sun never sets. Second, it doesn't maintain constant angular velocity. Third, it doesn't maintain constant size. Fourth, it rises considerably more north of where it should and sets considerably more north of where it should at equinox. Unless you can fix these problems on the flat Earth, literally nothing else matters. If you can't get the sun to rise where it should, set where it should, have that constant angular velocity that we observe in the real world, and the constant size, this can't be real. Now, I've heard a flat earther propose a solution to one or more of these problems, and that's atmospheric lensing. The idea that the atmosphere actually bends the light and makes the sun appear down here as opposed to where it really is, which is up here. Now, atmospheric lensing does really happen. So I can't deny that as a possibility. And Blender does allow you to put in lenses. And I considered trying to put in some lenses to see if I could get this to work. But I couldn't figure out a lensing system that would do everything needed. That lensing system has to take the sun from here and place it down here. But it has to do a lot more than that. It has to take it from over here and place it over here in the due west. It has to do more than that. It has to take this sun size and make it look the same as it did at noon. And it has to create constant angular velocity through the sky such that sundials work. Now, if you accomplish all that, I'll be impressed. However, the first thing I'm going to do is take this sun and move it to a different season. Either I'll move it to winter solstice or to summer solstice. And I'm going to check whether things still work in those seasons. And then, if that works, I'm going to take this observer, which is in the Salt Lake area, and I'm going to move him to Australia or to Africa or to South America. Bottom line, I'm going to move him around and see if your lensing system still works for everybody all over the globe. To recap, your lensing system has to get the sun to rise in the east and set in the west. That means you have to correct the bearing and elevation. You have to fix constant angular velocity through the sky. You have to make the sun a constant size as it travels through its path. If you're not convinced that the sun should stay a constant size, I can tell you, we can pretend that this is the moon instead, and you should feel sure that the size should be constant. Your lensing system has to work for all seasons, for all observers. If you accomplish all that, you have my profound respect. I think you're very smart. However, I would be back to faith at that point. I would be taking your word for it that such a complicated lensing system exists in reality. It's not something that I could ever prove or disprove with my skill set. Also, if you take that lensing system seriously, I would say, to be fair, I believe you should stop teasing globe earthers for inventing something called gravity to make their model work, when you have just created a very complicated system to make your model work. So, refusing to mock things such as gravity is just good consistency on your part if you accept this lensing system. Another thing I would say is that if such a thing exists in reality, I would ask God, why? Why did you do that? Why did you create a system which in every way was designed to fool me into thinking that the Earth was a globe and that the sun and moon path are angular? You created constant angular velocity, constant size. You made a system that works everywhere on the Earth. Why did you do that? It's almost like you were setting a trap. But I don't believe that. Let's talk briefly about stars, particularly in the southern hemisphere. Here are some national flags depicting the Southern Cross. Australia, Brazil, New Zealand, Papua New Guinea, Samoa, and these are at very disparate locations. This one, of course, is Australia. This is South America. If we come down here, we'll see one other interesting flag. Here's one in Africa. Now this is not a national flag and it's now defunct, but it also depicts the Southern Cross in Africa. Unsurprisingly, the Southern Cross is viewed by looking south. The Southern Cross is not at the exact South Pole. There's actually no very bright stars there. But when you're looking at the Southern Cross, you are looking southward. And the Southern Cross will typically be a prominent part of your star circle as you look south. Again, the Southern Cross is visible in Australia, South America, and Africa, all looking south at the same spot in the sky. That means their southern directions converge, a thing that is only possible on a globe. So let's talk about the star failure on the flat Earth model. Someone in South America is viewing the Southern Cross looking south. Which direction is south for them? Well, here's north. I guess south is dead opposite. South. And they'll see the Southern Cross off somewhere in the south doesn't move very far. It's a prominent part of their star circle. I guess that means that the Southern Cross is off this way. But wait, the Southern Cross is also on the Australian flag. What's their direction south? Well, here's north, so I guess south is off this way. They see the Southern Cross within a few degrees of their south. It's a prominent part of their star circle and doesn't stray from it. Guess that means that the Southern Cross is off this way instead. But once again, people in Africa see the Southern Cross. I guess that means the Southern Cross is off this way. I guess the only option on a flat Earth is to have 3 different Southern Crosses, at least, if not more. And to have very unusual little portions of the firmament that rotate here and here and here. It's a complication which I haven't seen most flat earthers try to address. And one more nail in the coffin for me thinking that this is reality, or a reasonable approximation to